Physics Notes, Unit 18C, Electric Force Fields, and they're in the same ballpark as gravitational force fields. The concept of fields in physics is referring to space surrounding something. Going back to gravitational force fields, there's all the space surrounding the Earth, all the way out to the moon and beyond, where the Earth's gravity influences things. It's in many ways, well, it's invisible. We can see what gravity does to things, but we can't see gravity itself. We really can't even feel gravity. As I sit in this chair, I'm not really feeling gravity. I'm feeling the chair as I sit on it. If I stand on the floor or lay on the floor or lay in my bed, I feel the bed. We feel things because gravity keeps us pulled against them. But that's another story. The Earth's gravitational field extends into three-dimensional space. So it's an invisible thing. So we have this challenge once again with fields that they're three-dimensional and they're invisible. And we have to represent them on a visible two-dimensional piece of paper. And what do? We use arrows. So let me go to the definitions here. Electric force fields. An electric force field is the space that surrounds an electric charge. And we have to use our minds here. Okay, and well, let me finish the definition. It's the space that surrounds an electric charge in which electric forces are acting and are present, similar to gravitational force fields. So we have to use our minds here. We have to envision charges. We can understand that an electron is negative. And we think of an electron as a little ball. It's probably not a little ball. Proton's probably not a little ball, but we can think of them that. So we have to draw them some way. We have to imagine them some way. We think of them as a little ball. Down here, this little blue thing is supposed to be an electron. And these arrows represent the influence that electrons have on a positive charge around it. It'll suck a positive charge in. Okay? And a proton will repel a positive charge. I'll talk about why these arrows point the way they do in a few minutes. But these are two separate diagrams. There's three separate diagrams. They're totally separate diagrams here. This diagram is independent of the other two. This represents the electric force field around that electron. It'll attract other positive charges. It'll repel negative charges because like charges repel. But we use these lines of force. Now let's talk about these lines of force. And we didn't really emphasize it much with gravitational force fields, but it's the same principle. Okay? So we use these lines of force to represent the field. The fields are 3D, as I mentioned, three-dimensional, even though we have to draw them on a two-dimensional piece of paper. All right, so they fill space. It's the space around these charges. And they're not imaginary charges, but we kind of have to imagine them because we can't see them. All right, so if we have an electron in space in front of us, I think of a little ball in front of me, even though it's not a little ball. Okay, and the direction, the convention, basically worldwide, internationally, in almost every book, the convention is we think of them as always pointing towards a negative. What we think of is a positive test charge. That's point number one right here. Let me circle this. We think of these imaginary positive test charges. Even though electrons are pretty small, we think of something even smaller. In other words, if I put a little positive, I think of it as a positive speck of dust right there. A positive speck of dust, my positive test charge. It'll get sucked in. It's kind of like, a rock gets sucked to the earth. Or anything gets sucked into the earth. Small things get sucked into the earth. If you just drop a ball, it falls straight in. So if I put a positive test charge anywhere here, or if I put it here, I could draw another line. I just can't draw millions of lines. I drew enough of them already, or somebody did. Anywhere I put a plus charge, it's going to get sucked in. Plus charge, plus charge. It's going to get sucked in straight toward, kind of like a ball dropping to the earth, because the earth pulls things in. Electrons pull in positive test charges. So these are defined in terms of positive test charges. Same thing for this second diagram here. If I put a plus charge right there, a tiny test charge, really small in mass. Okay, it doesn't affect the source. This is called the source charge. In this case, say a proton, a positive particle. It will repel. It'll go outward. So once again, the arrows are always defined in terms of which way would a positive test charge be repelled or attracted in that field. And over here, this is called a dipole. When you have two equal-sized charges. I'm not going to make you draw these in a book that has you drawing a few of these. There's a bunch more variations on these. Actually, I'll show you a few variations on these, but you should be familiar with these. I may ask you these general shapes or you might have to draw these in a lab, but on a test, it's going to be multiple choice. You have to pick which ones match up. We'll talk more about that. But it's called a dipole when the two are the same size. There's a lot of symmetry here. But notice also, once again, all the arrows point towards the negative and they're away from a positive. Some other things to keep in mind is you can draw all these lines. You could draw more lines in every diagram. But once you stop drawing them in any one of these diagrams, the closer compacted these lines are, means there's going to be larger forces. We're going to be calculating forces. And don't get scared. They're not that hard to calculate. Well, we've already done some calculating. Coulomb's law. We're going to do some more of that in a little bit. Anyway, the closer together the lines are, so you need to be familiar with that principle, the stronger the field is. So, for example, if I'm out, go back to this one on the far left. If I call this location B and this location A, okay, location A has a stronger field than location B because the two lines between are getting further apart at B. And the closer I get to that negative charge, the stronger the field. Same thing for the plus charge. Over here for the dipole, the strongest part of the field is right here between the two charges. And that makes some common sense. All right, the lines themselves are perpendicular to the surface of the charge. All right, they're perpendicular to the surface of the charge. If you look at those lines, well, it's hard to draw a little right angle, but I can draw right angle symbols. I'm drawing it on this positive charge right there. I drew some right angle symbols. Same thing is true on all the ones over here. The lines are perpendicular to the source of the field. So we call those the source of the field. Here's one source, here's one source, here's two sources. And you could have many sources, and you can have different shapes of sources. You can have, you'll see, line charges, parallel plates. We'll get to that in a little bit. In one sense of the word, certainly for the first two diagrams, it shows you the way a positive test charge will move, straight in or straight out. Over here, basically these curves kind of show you what a positive test charge would move for the most part. It would move along that line. For the most part, it'll move along that curve and get sucked into the negative, away from the positive toward the negative. So you can think of it that way. All right, so those are basic fields. That's the dipole, okay, a plus and minus of equal size. And this is also a dipole over here, a plus and minus of equal size. It's a very uniform field. Here you have two pluses. It shows you the two arrows repelling everything. For two minuses, two negatives, it'd be the same shape. Everything would be the same shape, except for the arrows would be pointing in. It shows you basically the direction that positive specks of dust would travel if you put them in there and let them travel and keep the source charges fixed. In diagram 3 here, you have a line. It's negatively charged. It's a bunch of negatives on there. A bunch of negatives on there. Okay, it's called a plate, flat plate. It could be three-dimensional, or it could be one-dimensional on a piece of paper. It could be like a pencil and a dot. Okay, but this would be the shape of the field, always towards a negative. This is the one that we're probably going to use the most right here. It's called parallel plates. In 3 dimensions, it's like two pieces of paper facing each other, but they're metal. Two rectangular plates facing each other, but metal. And one side is missing electrons, so it's positive, spread out, and this one's negative. The electrons are spread out. And once again, the arrows always point towards the negative. This is a uniform field. This is a uniform field. I say that right here. It's very important. Uniform fields are really nice. Symmetrical fields are nice, like the ones up here above. These first two are symmetrical. There's some uniformity to them, but they're not uniform in a sense everything is equally spaced parallel lines. Because this results in a force that varies as you get closer. The closer you get, the stronger the force is. The further away you get, the weaker the force is. But here, if you put an electron in there, or a proton, let's say I put a proton right here, put a proton, or put a positive speck of dust right there where I just labeled that, there'll be a constant force. And when you have a constant force, you'll have a constant acceleration. We can use our uniform acceleration equations from Physics 201, going back, and we will do that here in a few minutes. Sorry about that. You'll have to have your notes ready from Physics 201. Kinematics, uniform acceleration. So uniformity is nice. The calculations are much nicer when you have uniformity because it makes the calculations easier. So I've stated that there. Uniform force. So a proton will accelerate, in that diagram I just had, number 4, a proton will accelerate to the left. You put an electron in there, it'll accelerate to the right, uniformly. Okay, now, this is actual experimental data of the same thing. This first one is the dipole. The first one's the dipole. It's very uniform. This, I don't know which one's positive, which one's negative. I'll put the top one plus the bottom one minus. I don't know because there's no arrows on there. But if you look at the shape of what they have is they have an oil bath with some charged threads. Some charged threads in an oil bath, and they let them kind of stabilize. And if this is the negative on the bottom, if you I'm just following the path. It's the same diagram as the dipole I have up above. All right, and I put the arrows on there because I made the bottom one negative. So you'll see it's the same. I'm doing an okay job, not perfect. It should be all very symmetrical like diagram number 1, or let's see. Yeah, this one right here, diagram number 1, or the one way at the top, this one here. It's the same diagram, but a real experiment. And this is the one where it's repelling, and they could be both positive. If I made them both positive, it's the same diagram. If you look at the pattern there, it's the same diagram as this pattern right here. Once again, 2 negatives would give you the same pattern, but the arrows would be pointing the other way. All right. This one is the parallel plates. So what's true here, once again, if I make this one negative on the left, and I make the one on the right positive, and it really wouldn't matter. Okay, it just would change the arrows. There's a uniform field. That's the uniform field. We call that uniform field between parallel plates. What's important here, those are all supposed to be parallel. What happens is you get what are called fringe effects on the outside. We don't want to use the outside, but what happens is the field starts to not be uniform out here. So that's the part of the field that we don't normally talk about or don't want to use, but it's still there. And also true, it gets weak on the backside. Anywhere else, it starts to weaken. So it's weak over here. There's one question about that on the homework. What's true about the field over here? It's very weak. There's still a field there, but it's weak. It's very strong and uniform between the 2 plates. Here's one that's interesting. You have this plate, or a line, and you have a circle. And once again, if you make the left one negative, it doesn't matter which one's negative, it just changes the arrow directions, and make this one positive, but because the lines connect from one to the other, one is positive, one is negative. If you look at this one carefully, and look at the pattern, it looks something like this. Okay, I'm doing a decent job. But what you look at is there's no field, no pattern here. That's a very important concept. Inside a conductor, this has to be a conductor. There's no field. There's no pattern. There's no force. No field. No force. Okay, so no field and no force inside a conducting sphere or conducting metal. So no field, no force inside a 3-dimensional conductor. That's very important in electronics because you can shield from outside electrical interference. It's a shield. I think I wrote that down here somewhere. Yeah, shielding. So electric shielding, the electric field inside a 3D conductor is 0. I said it down here. It's useful in protecting electrical components because it shields you from outside interference. So it's important when in computers to shield the electrical components from sensitive interference from outside. You can shield your cell phone by putting it in a metal container. Cable TV cables, that cable that comes into your house has a shield around it, a tube of metal that shields it from interference. That's why you get good, supposedly good cable reception. If you're in here's another application of this. If you're inside a car, which is basically a metal box, there are some, I guess, fiberglass. I mean, Saturns used to be fiberglass, and I don't know if they made some Corvettes at one time that were fiberglass. That wouldn't count. If you're inside a metal car is like a metal container, it shields you from outside electrical interference. So bottom line, what that means is, like, if you're in an electrical storm, like lightning, one of the best places to be is in the car because it's a metal cage inside your safe, all right, and it's got rubber tires that are insulated. The problem is if you step outside the car and you're touching, now you got a problem. If you touch the ground at all, or you go outside the car and you're touching the car and the ground, bad news. Stay inside the car. Don't jump out of the car. Okay, you're going to get and touch the car at the same time. You got some trouble. Here's some example. It's called a Faraday cage. Michael Faraday is one of the guys who did some work on this. This is a guy, and it doesn't have to be, it's like your car doesn't have to be a complete metal container, because it's got windows and stuff like that, as long as it's a mostly, it's a 3D container that holds around you. Here's kind of a chicken wire fence around this guy, and the electrical strike hits that cage and it's grounded. It goes to the ground, doesn't affect him. He's safe inside that Faraday cage. So, because things inside are protected from the outside influence of electricity, or big damage from that electrical shock or electrical strike, lightning, and so forth. Stay inside your car if there's lightning. It's safe in there. And don't touch outside. Actually, a sad story. I had a friend of mine 3 years ago, his granddaughter, who was 19 years old, that happened to her. She actually was like, she hit a telephone pole or electrical pole, and the wire came down in the car, and she was safe while she was in the car, but then she tried to get out of the car and she got electrocuted. It was sad. So be careful if a wire falls on your car. You're safest to stay in the car until somebody comes and helps you. Okay, definition of electric field strength. The force exerted per unit of charge. All right, so this is a new concept. It's going to be interesting here. It's going to look a lot like, well, Faraday's law down here in this box. This is Faraday's law. This is previous. That's unit 18A. But here's a new definition, electric field. This is a definition. It's not a discovery. Faraday's law was a discovery. He figured that out. That's a law of nature. Electrostatic law of nature. Just like Newton's law of universal gravity is a law of nature based on quantities we can measure. But this here is a definition to help us apply and build electrical devices. But E is electric field strength, equals F, a force over a charge. We're going to practice this a lot because it's easy to get the two concepts confused. I guess they look a lot different in these equation forms, but what turns out is, because Faraday's law, which I'll double circle here, is that I can take this equation over here, and it turns out that E equals F over Q, so that's K sub E times Q1 times Q2 over R squared, all divided by Q. Okay, so basically what I did is I took this equation, I'll do a different color. All right, I took this equation, this expression, and I put it in for F. And then I brought it over here where I have this final result. You don't need to write all this down. This is more theoretical than I normally get. But what I'm showing you here is that once you put that all together, this Q over here on the far right, the one I just wrote down is kind of massive equation. That's Q2. All right. So bottom line is that Q2 cancels that. What I'm trying to prove to you is this, that E, electric field strength, is KQ1 over R squared. So there's a third equation here, which is really, I'm combining these two equations over here in a circle. So that's one of the most theoretical things I've done this year. Well, in this term, proving to you that this equation is a combination of those first two equations. This is looking kind of messy to me, so I'm going to kind of erase most of that. Whoops. I could have left that there. But the important thing is that equation, this equation, those three circles. We're going to be using those three. We've already used Coulomb's law. Now we're going to use E equals F over Q, and we're also going to use E equals KQ over R squared. This Q right here is Q1. It's the source of and I really don't need to put the subscript there, but it's Q sub 1. Let me show you what I mean by that. Now, what can be confusing is those two equations look a lot different, but they give you basically the same result, and the question is, when do you use which one? For example, question number 1 right here. Determine the electric field strength. Well, first of all, I'm looking for E, not F. That's what on the next test, that's the first thing you have to determine. Am I looking for E or F? It says electric field strength. That's E, not force. If it says force, then I'm going to use this equation right here. Typically, well, this also has force in it, so hang on to your hats there as well. But electric field strength, 25 centimeters from a 12 microcoulomb charge. Well, it's asking for E, and it gives you a distance. So we're going to use this equation over here. We're going to use the E equals KQ over R squared, since this gave us R. So I'm finding E is 9 times 10 to the 9th, still same as before, times Q, well, 12 micro. It's 12 times 10 to the negative 6. I could have just put the micro symbol on there. Divided by 0.25 squared. Once again, don't forget the square on that, and don't forget to put that in meters. So if you do the math there in this case, you get 1.7 times 10 to the 6th newtons per coulomb. That's the electric field strength. And if you had to draw it, it'd be like that positive one, that diagram number 2 at the very top, for that red plus charge for the field. It's just all these radial lines outward, like the sun, giving off rays into space around this charge. So that's the electric field strength at that distance from that charge. Now, so determine the electric field strength for a 3 microcoulomb charge that experiences a force of 2.5 newtons. So because I just used that second equation, it's probably the first equation, which it is. It's just a straight application of E equals F over Q. It says there's a force on a charge. It tells you the force is 2.5 newtons. That's good units. Divided by the charge, 3.0 times 10 to the negative 6th. So that charge is experiencing a force of 2.5. You just plug that in. So you get E equals 8.3 times 10 to the 5th newtons per coulomb. I just realized one thing too, that it was not quite right that I said a few minutes ago. If I go way back up here to the top, technically up here at the top, this is supposed to be Q2. Sorry, that's Q2. That's the one that cancels out. That's the one I just used. Okay, I said it over here. I put it. It really is kind of a subtlety. All right. So here's where you have a charge in the field that would cancel out of this equation. This equation is when you know what the source of it is. This is for the source. Q is like the source, that central charge. All right. This problem we just did was a charge that was in the field. The 3 microcoulombs wasn't the source of the field. It was feeling the force. It was somewhere in the field. For example, if my source was a plus charge, which I don't know what it was right now, this could have been my diagram for problem number 1. Okay, this is my field diagram for problem number 1 that I was talking about, radial outward. This problem is saying, okay, you've got a charge. You don't know what the central charge is. You know what your Q2 is. That's your test particle, your 3 microcoulomb charge out there, and it says it has a force. I don't know which direction the force is. Oh, and near another positive charge. So I know the force is indeed this way, and the force was 2.5 newtons. But that is indeed Q2. I don't know what Q1 is here. Yeah, I could figure it out. So if they ask you to figure out what Q1 is, you could just go back to this equation, because we know Q2, we know the distance, we know the force, we know everything but Q1. That'd be another good question for a test. Anyways, number 3. How far from a 30 microcoulomb charge is the field 2 times 10 to the 6th newtons per coulomb? Anytime they have distance, you're going to be using that second equation, because the first equation doesn't have distance. So we have KQ1, so now we're looking for the source, over R squared. So we're looking for R. It says E, the E field is 2 times 10, or assuming these all have 2 or 3 sig figs. In this term, everything we put down here is going to have 2 or 3 sig figs. Don't go past 3 sig figs, though. It's really not going to be that important anyways in this class. It's important. It's an important consideration if you're an actual research scientist or doing work. You got to pay attention to sig figs. Don't get crazy. Times Q1, so 30 times 10 to the negative 6, not 3 times 10 to the negative, 30 times 10 to the negative 6, 30 micro, divided by R squared. So R squared is going to be the 9 times 10 to the 9th. I could have done some of that work already. 30 times 10 to the negative 6th divided by 2 times 10 to the 6th. So I'm going to do the math there. So I multiply all those. I multiply those numbers together on top and divide by the bottom. Then I have to take the square root. So that's what I'm going to be doing. The last step would be to take the square root. So if you do all that, well, r squared, before I take the square root, is 0.135. That's when I multiply the 9 times 10 to the 9th times the 30 times 10 to the negative 6 and divide by the 2 times 10 to the 6th. And then you take the square root, you end up with 0.37 meters. So 37 centimeters. That's how far apart, or how far that charge is, or how far the distance is to get that particular field. For electric fields, we don't know, well, there might not be anything out there. We know what the source is in the middle, but what's on the outside, what's in the field, we don't know. It could be nothing, it could be something. And number 2, we knew there was a charge in the field. The 3 microcoulomb charge was in the field, but here it just says the field is this at that distance, or at what distance would the field be that. There may or may not be some charge at that location. Okay, number 4. All right, so I drew a little bit for number 4 here. You have a 6 microcoulomb, and a negative 6. There's 2 of them here. Oops. There's a positive 6 and a negative 6 microcoulomb charge separated by 60 centimeters. A lot of 6s. All right, I'll put the 60 in later. It's asking for the electric field at a point midway between them. Once again, this is an electric dipole, and we want the electric field right there. We need the specific numerical answer. There's nothing there. It's a location. So in electric fields, there may or may not be a Q2 at that location. The only one so far was problem number 2, which was the Q2. Here we have 2 Q1s that are both the source of a field, and they each generate. What we're going to have to do is we're going to do an E1. Okay, due to the positive 6. In other words, and it's a vector problem. All right. So for this positive 6, you got to think of radial lines coming out. But I don't want to draw the 10 lines coming out. I don't want to draw this diagram. I'm just going to get dizzy here. Go to the way top. I don't want to draw this diagram every time. This one here. For that positive 6, we're talking about a location like right over here to the right of that. So if you were to draw one line, it would come out to the right. It would go like this. All right. And I can put that arrow anywhere, and I don't have to draw that arrow, that whole arrow that long. So what I'm going to do in the problem I'm doing right now is I'm going to draw just the part of the field that's right there. Part of the arrow that's to the right. That's what we do. I don't want to draw all 12 of these lines. It's too much. Don't need to. So in other words, and it's always away from the plus. So this is going to be what I call E sub 1. E sub 1. That says E sub 1 there. All right, I got the 1. Well, E sub 1 is KQ1 over R squared. Well, E sub 1 from that 6, the positive 6, is 9 times 10 to the 9th times that charge, which is what? 6 microcoulombs. So remember, 6 times 10 to the negative 6. Now the distance is 30 centimeters because I'm halfway between the two, 0.30 squared. So E sub 1 equals, whatever that computation is, I think I did it earlier, 6 times 10 to the 5th newtons per coulomb. 6.0 times 10 to the 5th newtons per coulomb. And I drew it on the diagram. It's an arrow to the right. This arrow right here. That's the size of that, 6.0. The interesting thing here is E sub 2 is KQ2 over R squared. Now, it's kind of nice to you on this problem. That's Q sub 2, not Q squared. And the bottom thing is, I'm getting sloppy here. That's an R, not a V. My R sometimes look like a V. That's R squared. The thing is, okay, from my negative 6 microcoulomb charge, E2, I should have drawn it the same length. All right, it's the same length because E sub 2, now E sub 2 is to the right because of the negative. Electric fields point towards negatives. So that's why the blue one points towards the negative 6. The negative 6 is a negative charge. I'll put a blue dot there for that negative 6. But the thing is, it's the same distance. The only thing that's different is the negative. You don't put negatives in these equations. The only thing that's different is the negative, but everything else is the same, gives you the same answer. So E2, E sub 2 is also 6.0, not negative 6.0. 6.0, okay, times 10 to the 5th. Newtons per coulomb. So what is E total? We want the E total. I got to add up those two vectors, E total. Well, that's pretty easy because they're both to the right. So it's going to be 12.0 times 10 to the 5th newtons per coulomb to the right. That's my answer. And you could put it in standard form. That's not standard form, but that's fine. It'd be 1.2 times 10 to the 6th newtons per coulomb. But 12 times 10 to the 5th newtons per coulomb is the same as 1.2 times 10 to the 6th. But you got to say to the right. So this problem is easy in the sense that because the first one has the same magnitude and the same distance, you just basically double that 6 and get 12. Now this one's a little bit harder. Part B is harder. So let me do part B. It's quite a bit harder, as you'll see. In part B, I may need to erase parts of part A. So we have our 6 micro. Oops, that's not negative 6. The one on the left is the positive 6 microcoulombs. And then we have our minus 6 microcoulombs. In part B now, it's talking about a spot, a location up here. It forms basically an equilateral triangle. In other words, that distance is 60 centimeters. So still the 60 centimeters. And this distance is 60 centimeters. So there's a lot of symmetry still, which is going to help us. And I'm going to erase some of this stuff over here on the right so I can... So get ready. You might want to take a screen... pause this, and I'm going to erase everything else. Okay. Or go back if you have to. All right. I'll leave the equation up there, though. All right. So, but the same kind of idea applies in the sense that we have the same charges at the same distance, but you have to line these up. In other words, this E1 is in that direction, and now it's always away from the positive and directly towards the negative, but E1 and E2 will have the same size. E1 and E2 will have the same size still. The directions are just kind of goofy here. It's going to be harder. It's a harder vector problem because they're not lined up. And they're not opposed to each other, not directly opposed, so you can't just subtract them either. We might have to use components. Ooh, that's a dirty word for some of us. But this problem is not as bad as you think. Well, maybe it is. I don't know. I don't think. I love this kind of stuff. This is the kind of stuff I like about physics. Some people don't, but that's okay. Different strokes for different folks. But to recalculate the new E1 for this diagram, it's 9 times 10 to the 9th times 6 micro, same as before, but now it's a bigger, no, it's the same, no, it's a bigger distance. It's 0.60. It was 0.30 on the first problem, squared. So E1 equals 1.5 times 10 to the 5th newtons per coulomb. I'm going to circle that. It's not the final answer. But E2 is that same number. E2 also is 1.5 times 10 to the 5th newtons per coulomb. They're the same. But I can't just add 1.5 and 1.5 and get 3.0 because they're not lined up. Rats. So how do I add those two vectors? Well, there's a lot of symmetry here. If you look at this, if you remember this from algebra, all right, if you have, basically there's the two sides here are 60 and 60 and the bottom is 60. This is an equilateral triangle. In other words, I'm going to draw the triangle shape of the configuration like this. All right, that's the triangle shape of the configuration. 60 degrees, 60 degrees. In other words, I have my positive 6 microcoulombs here. I got my negative 6 microcoulombs down there. I'm just transferring from way over here. I'm not going to draw on top of that one. And then the location I'm talking about is up here at the top. And I've got my E1 up like that. And I got my E2 like this. Let me use blue. Come on, blue. And I got my E2 like this. But the E1 and E2 are the same. But the thing is, if I draw a horizontal line right here, I draw a horizontal line right there. This angle right here is 60 degrees. That's kind of nice. It's going to help me a lot. It's 60 degrees above that line and 60 degrees below that line. There's symmetry here. So both those E1 and E2 are at a 60 degree angle with respect to a horizontal. Let me clean that up a little bit. All right, so that's... Okay, we'll go back to red. So this is E1. I know E1 is 1.5 times 10 to the 5th. But here's where we can go a little faster now. We do have to look at components though. We have to look at components. I'm going to draw E sub 1. E sub 1 has two components. All right, it has the horizontal component and a vertical component. So that E sub 1, okay, this is 60 degrees. So I'm just drawing E sub 1, which is 1.5. They're both 1.5. 1.5 times 10 to the 5th. All right, that's the horizontal component. And actually, if I draw E sub 2, here's why this comes easy. Because E sub 2, I'll draw it in blue. Because E sub 2 I drew as a blue vector, just kind of give you a perspective here. E sub 2 is angled down this way. It has this component. Let me draw it the right size. I want to draw everything the same size as the first one. That's supposed to be E sub 2, E sub 2x, E sub 2y. Alright? This is E sub 2y, E sub 2x. But some of you might be able to see this now more clearly already, now that I drew that blue one. I didn't really need to draw that blue diagram down there. This is E sub 1y, E sub 1x. It says E sub 1x. What you hopefully can observe here, E sub 1x, is that the y, since these are equal size vectors at the same angles, the vertical component of E sub 1 will be the same as the vertical component of E sub 2. Those are going to cancel. What's not going to cancel is the x component. So all I have to do is get the x component. I'm going to go up this red diagram up here. If I take the sine of 60, because this right side, this is the same, no, cosine. I don't want that over there. I want this I want the x component. If I take the cosine of 60, if I take the cosine of 60 degrees, that's going to be E sub 1x over E sub 1. Let me draw it down here. It's going to be cosine of 60 degrees, equals E sub 1x over, and I know E sub 1 is 1.5 times 10 to the 5th newtons per coulomb. Well, I look up cosine of, well, punch in my calculator, cosine of 60 is actually 0.5. It turns out that E sub 1x is going to be 7.5, if you do the math there, times 10 to the 4th newtons per coulomb. That's E sub 1x. That's the x component of E sub 1. The y component, I don't really care what it is. The y components will cancel. Y components cancel. Okay, that's for this problem for that problem up here. I'm not doing problem 5 yet. But there's two equal x components. All I gotta do is double that answer. I just need a double. Okay, double this for the answer. Because E sub 2x will be the same size. So the final answer is E total, E final. E total will be equal to 2 times that. So that's, well, it's going to be 15 times 10 to the 4th newtons per coulomb, which would be 1.5 times 10 to the 5th. It's a little bit not completely coincidental that it's the same as E sub 1. It's because of the 60-degree angle. But you could say it's 15 times 10 to the 4th newtons per coulomb, or what did I say? 15 times 10 to the 4th newtons per coulomb, or 1.5 times 10 to the 5th newtons per coulomb. Same answer. Oh, you should say to the right to give you the full picture of that. All right. So I doubled the E sub 1x because both E sub 1 and E sub 2 have the same magnitude. That's how you add those two. When they're lined up like that, you add them up, the other two canceled. So there we go. I'm going to pause this video and finish up the last 4 problems in part B of this lecture.